In this video, we're given the mass of the Earth and we're given the radius of the Earth. And our goal is to compute the acceleration induced by gravity as long as we're close to the surface of the Earth. So what we're after here is little g, and we're used to at this point taking the accepted value of little g to be 9.8 or to more sig figs 9.81 meters per second squared. And this is the acceleration of any free-falling body reasonably close to the surface of the Earth. And we're ignoring drag forces when we do those problems. So the way to get a handle on this is to introduce a little mass near the surface of the Earth. We'll call it lowercase m. And sometimes we refer to that as a test mass. It's just there to allow us to do force calculations. And if all goes well, it's going to cancel out in the end. And that test mass feels a force pointed toward the center of the Earth. And I'll call that capital Fg. That's a gravitational force. That gravitational force is given by Newton's law of gravitation. We're using the astronomical symbol for the Earth here, so a circle with a plus in it. So there's Newton's law of gravitation, g times the product of the masses divided by their separation distance squared, where g is about 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So there's the force exerted on the test mass, and a key assumption that we're making here is that that test mass is close enough to the surface of the Earth that we can approximate its distance from the center of the Earth with the radius of the Earth itself. And to put this in perspective, if you've ever looked at a picture taken from space where you can see Earth's atmosphere up here, it appears incredibly thin. And actually, the comparison that I've heard is that if you lay a dollar bill on a standard 12-inch globe, that's about the thickness of the atmosphere. So no matter how high you go in our atmosphere, you're basically at the surface of the Earth in terms of a percentage difference compared to the radius of the Earth, which is 6,371 kilometers. So we should be making a pretty good approximation here by saying our test mass is sitting right at the radius of the Earth. And then we apply Newton's second law, and we're applying that to the test mass. Fnet equals ma, and there's only one force acting on the test mass. It's the force of gravity pointing toward the center of the Earth. So we plug in that gravitational force, and that's going to be equal to the size of that test mass times its acceleration. And the acceleration of something that's in free fall, well, it gets the special symbol g, and that's what we're trying to compute here. So I'm going to go ahead and call it g. And the test masses cancel out now, which means it doesn't matter what the size of the mass is. The rate of acceleration is going to be the same. And I'll go ahead and solve for g on the left-hand side, and we can start plugging in numbers here. So big G, the gravitational constant, is 6.67 times 10 to the negative 11. The mass of the Earth was given to us to way too many sig figs. So I'll just keep maybe one extra. So I'll call it 5.972 times 10 to the 24 kilograms. And then the radius of the Earth is given to us in kilometers, and that has to be changed to meters. We can do that just by tacking on 3 zeros. Or if you prefer, you could write it in scientific notation. Okay, so we smash the numbers into our calculator, and I get 9.814 out of this. 9.814, or rounding to 3 significant digits, 9.81 meters per second squared. And so after using little g for so long to solve dynamics problems, we finally know where it comes from. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.